So the general format of a second order system can be represented in the transfer function format. This is output divided by the input. Okay, C of s by R of s. This is equal to the omega n square over s square plus 2 times zeta into omega n into s plus the omega n square. So how to get this? This can be easily obtained for the feedback system, which is represented in the following form. So R of s is the input. This is given to a summing block. This goes to the forward transfer function, that is the g of s denoted as omega n square over s into this is s plus 2 times zeta into omega n. This is the forward path B. All right, this provides the output denoted by C of s. And there is a feedback, that is h of s, which is 1. So this is unity feedback. So if you try to represent a negative feedback system of this type, I know that I can directly find the total transfer function as that's g by 1 plus gh, right? So definitely we'll simplify. When you simplify that, you get this. Okay, so substitute g of s as shown here, h of s as 1, and simplify, we get this one. So that's why this is called as a second order. The overall transfer function looks like C of s by R of s, which is denoted by that. So wherein we have the specific terms, that is one is omega n, right, which is present in the numerator as well as denominator. This is called as the undamped natural frequency. Right, we'll see the meaning of the word damped, undamped, etc. We'll see that later. Okay, and there is another term, that is the zeta. This is called as a damping ratio. So if you remember the first order system, what are the characteristics of a first order system? Which coefficients define the first order system? Just to check that, if you remember K and T, right? So K is the gain of the system, T is the delay, right? Or what do you call? What was the term in your notes? It's a time constant, right? So it is a time taken by the system to reach 1 by E times the actual response, right? So that's how you define that. Okay, so those two are the parameters which define the first order system's characteristics. Similarly, the two terms or two components which define the second order systems, right, is one is a damping ratio, other one is the undamped natural frequency. All right, now let's look at the various properties of the system before we go for the outputs. In order to look at the output, we need some more inputs. Okay, so let's define. So let's look at the characteristic equation, that is 1 plus gh. Okay, so I'll write characteristic equation is basically 1 plus g of s into h of s equal to 0. So that's actually the denominator of the given equation, right? So in the above transfer function, you see that denominator, that is s squared plus 2 times zeta into omega ns plus omega n square equal to 0. All right, so we know it's a quadratic term, so we can simply calculate for the roots. So s is equal to, we get two roots, right? Again, by applying the simple function, right? B square minus 4ac root of 4ac whole divided by 2a. Correct. When you do that, you get the following, that is minus zeta omega n plus or minus the j times root of omega n square into 1 minus zeta square. Okay, so this is what we get. Now for the time being, let's equate that to minus of alpha plus or minus j times omega times d. Okay, so here the omega d is, right, nothing but the root of omega n square. Actually, the omega n square can be taken out. So here alpha is equal to the zeta times omega n, and omega d is equal to omega n into root of 1 minus zeta square, correct? So we define one term here itself, right? Depending upon the zeta value and omega n value, I can generate another term, that is omega d. It is called as the damped natural frequency. Okay, so that is what is called as the damped natural frequency. Sorry. Yeah. It was for a while. I logged out. So can you hear now? All right. So this is called as the damped natural frequency, omega d, which is defined in this way. Now let's look at the same thing in a different fashion, right? This gives you a, yeah, when you substitute this value, right? So let us try to substitute. See, there is a 4 times, let me write. So let's write this term. So the S is equal to, you see that there is a minus, this is 2 times zeta omega n plus or minus root of, right, 4 zeta square omega n square minus, this is 4 omega n square whole divided by 2a. Okay, a is 1, sorry, I think. So you can simply write this as divided by 2 into 1. Okay, now you, when I try to take that 2 outside, so in this case, right, this, normally you see that the zeta value is, I use a property here, zeta is actually between 1 and 0, right? So zeta is the value which is always between 1 and 0. So you see that the first term is smaller than the second term. So 4 times zeta square into omega n square, right, is like that. All right. So that means this is a negative number, right? So I have to apply. Okay, fine. Now let's look at the above term. So I got a alpha plus or minus j times omega d, which is nothing but, so this is minus of zeta omega n, right, plus or minus j times omega n into root of 1 minus zeta square. Okay, now let's try to look exactly what is happening, right, to the poles of this system, right, when we vary the zeta value, because zeta is a damping ratio, omega n is fixed for a given system. Omega n is its response, whatever is the natural frequency. So if you remember the basics we studied from physics, it says that every body has its own natural frequency, right? It's something like you try to uh, give an input of that frequency, it tries to respond back to you with the same frequency. Only it happens whenever it's something similar to the resonance part. All right. So we know that the omega n is fixed for a given object or given system. Zeta is the one which we can change whenever we want to design something. Okay. Right. So considering that, now let's look at a graph. This is the real part. All right. So I can call this sigma. This is the S domain. So sigma and j omega are the two axes, correct? Fine. Now let us consider a when zeta equal to 0. If I say the zeta is 0, what's going to happen to the uh, root? This is actually s, right? So whatever equation you see, this is s, the roots of the equation, imaginary root. So it starts from here. Let me say the first one is plus j whatever, it simply becomes j omega n, correct? And I'll get a minus root, that's a minus j omega n. This is when zeta is equal to 0, which corresponds to no damping, correct? The terminology will discuss once again later, but if I'll tell the two terms, one is zeta 0, there is damping ratio is 0, so this is undamped. The system becomes, there is no damping. Okay, now the highest possible value of zeta is 1. Okay, so put zeta equal to 1 and tell me what's going to happen. Zeta is 1, so this term is 1, only real part, and the answer is minus omega n, correct? So okay, let me mark that over here. So that's right. You see, this distance is equal to this distance, is actually equal to this distance, right? Whatever I'm writing, the magnitude is same. All right, so I'll write a value here. This is minus of omega n, and this comes into picture when zeta equal to 1. So the other two cases, this and this, is when zeta equal to 0. And one more thing I just wrote when we derived that equation, right? The roots of the system, s equal to something we just wrote, right? There I told that zeta varies actually between 0 and 1. It's neither 0, it's nor 1. It's always between. So you see that when it was 0, close to 0, you are having two roots, right? Properly on imaginary axis. As you increase the zeta, right, it should come closer and closer, and it should reach the omega n, correct? Because omega n is the other extreme, isn't it? So for, as you can see, for the smaller values of zeta, it's actually at the vertical axis, close to 0. Close to 1, it will come and occupy the real axis. So for any other value of zeta, I'll mark another point. Okay, I'll mark a point which has a zeta value between 0 and 1. Okay, so let's say that that value is somewhere over here. Okay, corresponding to this point, I'm going to have an equivalent point on the other side. That's the negative of this axis. Okay, all right, now you see the zeta is neither 0 nor 1, it is between. Whenever it is between, the coordinate of that point should be, what is the x coordinate of that particular uh, root? So I can write this is, say, s1, the other root is s2, because you have two roots, correct, of the equation. So this is going to have, so this value, what is this coordinate? It is minus zeta into omega n. It's because it's neither properly 0 nor minus omega n. It's between that, correct? So that's why it is minus zeta omega n. And the y coordinates are given, right? One is plus j times zeta into not zeta, omega n into root of 1 minus zeta square. Other one should be minus j times omega n into root of 1 minus zeta square. Are you okay? That's now you see this whole thing is coming. Okay, this is one point. In the sense, whenever the zeta is between 0 and 1, we have the roots occupying the negative half of the s-plane somewhere between the 2 points which we marked as extremes, right? So the extreme points are this. When zeta is 0, this is the other extreme point, wherein you are going to have two roots, right? Both will match the same omega n, minus omega n. Okay, right, now let's go to another point here. So let me draw one of this, let me connect this to the origin. Okay, so what is this distance? What is the length of this line, this chord? Can you tell me? Only length. Length is obviously correct. So that is omega n. I'll write this. So this is this length is omega n. If I try to draw a right angle triangle over here using the sides, now can you tell me what is this distance? Magnitude is just zeta omega n, zeta into omega n. So since it is on the left hand side, x-axis, the coordinate is minus zeta omega n, but the length is zeta omega n. All right, are you okay? All right, now can you tell me what is this angle theta? Theta is specifically measured with respect to x-axis. Always we measure the angles with respect to the real axis. Okay, so what is this angle theta? Can you try to define? Yeah, okay. Right. So tan inverse, if you want to use this, is omega n into root of 1 minus zeta square whole divided by the adjacent, which is zeta into omega n. So omega n cancels, so your ratio becomes tan inverse of root of 1 minus zeta square whole divided by the zeta. Okay. Right. Again, in problems, you are going to see that you need the other ratios as well. So can you tell me in terms of cos? What about cos inverse? Yeah. Correct. So it's simply, you see that omega n cancels. So in simple, most simple ratio is cos inverse. It's simply cos inverse of zeta. All right. So definitely we might require the sine as well. So this is equal to, if I want to find sine inverse ratio, this is the opposite. Opposite is nothing but omega n into root of 1 minus zeta square whole divided by the omega n, right, which is the hypotenuse. So this is sine inverse of I think root of 1 minus zeta square. All right, so these are the three things, right, we require from this. So whenever you are considering a second order system, depending upon the zeta value, the poles will occupy, right, different positions on the left hand side of the S plane. They trace out a half circle, semicircle, right, on the left hand side. That's the first point. Second thing is we can write it assuming that the poles make an angle theta with respect to the x-axis, right? Theta can be found using these two, the three different ratios, trigonometric ratios. Okay, now let's go to the different conditions now. So let us consider a situation wherein we are going to consider the first case, right? We are going to look at the response now. Okay, so this is the first response of a second order system to step input. Okay, so now we are writing the same second order system which I already wrote, the second order systems model, the transfer function and the block diagram. Already I have written, so I'll skip that for the time being, but when you answer you can write it here. Okay, so I'll directly start from this, the C of S by R of S of a second order system in general is nothing but the omega n square whole divided by s square plus 2 times zeta omega n s plus omega n square with the standard notation. Zeta is a damping ratio, omega n is a natural frequency, undamped natural frequency. So if, say, R of s is equal to 1 by s, it's obvious because we are providing the step input. Unit step input is see, impulse response is straightforward. Impulse response in the sense, this transfer function itself is impulse response because when the input is impulse, right? What is the Laplace transform of impulse? It is simply 1, correct? So you see, what happens to C of S? C of S is equal to transfer function into 1. So that itself, that's why the impulse response is not considered. So in general, it's not only for this. Okay, whenever somebody says that, okay, what is the impulse response? It means it is a transfer function. Okay, any system, digital, analog, or doesn't matter what what we are talking about, irrespective of what uh, system we are considering, transfer function itself is the impulse response. Okay, so that's why we directly go to the step here. All right. So step means R of S is 1. So this implies the C of S is equal to, right, the transfer function, whatever, T of S into R of S. Right. So this is what we are writing it as a T of S. Okay. Now let's write the term. So this is equal to the omega n square whole divided by the S which comes because of R of S in the denominator. I'm writing here into this is S square plus 2 times zeta omega n into S plus omega n square. Okay, now we can actually write this as, right, we can actually split this into the following format, right? Again, we need to write the partial fractions. Directly I'll write the answer. Okay, you can apply the partial fractions to get this 1 by S, and the numerator is, this is S plus 2 times zeta omega n whole divided by this part, that is S square plus 2 times zeta omega ns plus omega n square. All right, so this means now, okay, let's try to make a perfect square somewhere. All right, so because of which I'm going to write this as, this is 1 by S minus, for this term, there are 2 times zeta omega n. So let me write it in this way. This is, we'll split this as zeta omega n plus zeta times omega n whole divided by, so let's split. This is S square plus, I'll try to, okay, 2 times zeta omega n S plus omega n square. I add and subtract the zeta square omega n square minus zeta square omega n square. Okay, now this is nothing but 1 by S. Right, okay, this is minus. Now I'll club the zeta square omega n square with the first term. Okay, I can write it in this way. This is S plus zeta times omega n, and I'll separate the zeta times omega n whole divided by. So I can write it in, see, this form. This is S plus the zeta omega n the whole square, and I'll club the omega n square and this term. These two terms I'll club. Okay, so when I club the omega n square and the minus zeta square omega n square, I can take the omega n square outside and I can write it as 1 minus zeta square. Okay, so this means I know some of the terms here. So this is actually the 1 by S, and okay, this is minus, okay, let's substitute. This is S plus zeta omega n, numerator as it is, no change. Okay, plus zeta omega n whole divided by, this is S plus zeta omega n the whole square. What is this term? What is this term in the denominator? Omega square, omega n square into 1 minus zeta square. If you remember, omega d, right? So I can call it as omega d square. All right, so that is the damped natural frequency which we already defined. Okay, so in the next step, I just want to go back, right? I want to go back to the time domain. So my intention is to bring this into, modify this in such a way that maybe we'll try to get the standard inverse Laplace. As of now, only the first term has inverse Laplace, correct? Only that has inverse Laplace. It is u of t, right? But the this term I need to bring it into some standard format so that I can take the inverse. For that reason, let's do something. this part I can write as, okay, so let's do one thing. So this is 1 by s. Let's split this into two different terms. Okay, the first term is minus s plus zeta omega n whole divided by, this is denominator remains same, and that is s plus zeta omega n the whole square plus omega d square, and the next term is what is that, zeta omega n whole divided by s plus zeta omega whole square plus omega d square. Now, can you get a standard inverse for this? Yeah, I think this is standard, right? S plus a divided by s plus a plus a term omega whole square. It's there. So this is standard. I don't have to do anything with the second term. So we got one more term now. So first and second term, they are standard. I need to do something with the third term. So what can we do? If I omega d square I have, so I need to bring a omega d in the numerator. Okay, that's possible. 1 by s minus s plus zeta omega n whole divided by, this is s plus zeta omega n the whole square plus omega d square. Okay, this is done. Minus, now I'll take, anyway, I need the zeta as it is. Anyway, zeta has nothing to do with that. If I want a omega d in the numerator, I should multiply and divide by root of 1 minus zeta square, correct? Because I already have a omega n over there in the numerator. To cancel this, I divide by root of 1 minus zeta square. Okay, this and this is what is the addition I'm doing now. So I multiply and I divide by. Let's keep the denominator as it is. That is s plus zeta omega n whole square plus omega d square. Okay, I think, yeah. So now we can write this as 1 by s minus, this is s plus zeta omega n whole divided by, this is s plus zeta omega n whole square plus omega d square minus zeta by root of 1 minus zeta square into, this is omega d divided by, okay, the same thing, s plus zeta omega n whole square plus omega d square. Okay, so this is actually the C of s, right? So directly apply the Laplace inverse for the whole equation. So C of s will be written as C of t is equal to, so there is 1 by s, which becomes 1 minus, now this is this becomes what, sine or cos? This is s plus a by s plus a. S plus yeah, so this becomes a cosine term. So it is e to the power minus zeta times omega n. It's a, whatever a I can see, I am writing zeta omega n into t times cos bt. So b is omega d, so this is omega d into t. All right, minus zeta divided by root of 1 minus zeta squared into, this is e to the power minus zeta omega n t into, so this is b divided by s plus a whole square plus b square should be sine omega. Okay, sine function, sine of omega d to t. Now, so okay, what if I want to take this term common, right? So I want to take out this term from the whole. So what I can write is, I'll write 1 minus, I can even see that e to the power minus zeta omega n t is common, out of which and in the denominator I'll try to take out 1 minus zeta square. Okay, this means I should multiply to the first cos term as a root of 1 minus zeta square into this is cos omega dt minus this is zeta into sine of omega dt. Uh, isn't it? Okay, this is fine. Now let's go back and check what is this term and what is this term. Can you tell? Because we already know something which is pretty much defined, right? Use this and this to define simply zeta and root of 1 minus zeta, right? So, right. So this is a cosine function and the other one is a sine function. So let's substitute that. So this is equal to, this is 1 minus e to the minus of zeta omega n into t whole divided by root of 1 minus zeta squared times. So the first term becomes a sine function, right? So this is sine theta into cos omega d into t. I think minus is already taken off, so this becomes a plus. Sorry, this is plus cos theta into sine of omega dt, right? So sine a cos b, cos a sine b, sine of a plus b, right? Directly I can write that now. So this is equal to 1 minus e to the power minus zeta omega nt whole divided by root of 1 minus zeta square into sine of omega dt. I'll take this as a plus theta. So this is my equation. But anyway, in general, we don't know what is this theta, right? So you can actually, the textbook will say that you don't keep it in the form of theta because this is the response of a second order system, and every second order system is defined by omega n and zeta itself. So the throughout, right, whatever you see, it should be in terms of omega n and zeta as far as possible. So therefore I'll write a final answer. Okay, therefore C of t is equal to, this is what is the most preferred way of writing in the expanded format. You see, this is zeta omega n t. We are fine with this because standard notation, 1 minus zeta square. This is also standard. So into sine of, don't write omega d, you write the omega n root of 1 minus zeta square times t, because these are the two terms which define the second order system. Plus you can substitute for theta in any of the format, maybe tan inverse, right? I prefer cos inverse because it's simply cos inverse of zeta, right? So this is the standard output that we are going to get for a second order system whenever you give the input in the unit step format. Okay, so unit step gives you this answer, right? Provided the zeta is between 0 and 1. It's very important that the value has to be between 0 and 1. So this is what is called as the underdamped case, right? I think is term. Okay, I'll add a point here, right? This 0 less than zeta less than 1, this is the specific condition called underdamped system. Right. So quickly we go for the other cases as well, and then we'll come back to the same underdamped case, and we'll see why it is so important, because we discuss only about underdamped case always. We don't discuss about the other possibilities. Okay. So the first case is that zeta equal to 0 normally. We should start from there. But anyway, since there the zeta is equal to 0, zeta equal to 1, or zeta greater than 1 are not widely used, because such systems do not exist, and even if it exists, we try to avoid them, right? For some reason, I'll come to that later. Okay, so now the next case is, let's say the zeta is equal to 0, right? This system is called as undamped, no damping. Zeta is 0 means no damping, right? Yeah, you can directly write that in the required equation, and you can write it over there, right? But when zeta is 0, what is the value of the theta value? Theta 0, right? Zeta is 0, so sine inverse of 0 is 0. So you have only real part, correct? The s becomes equal to simply minus omega n, isn't it? Uh, in the previously written diagram, we can refer that. It comes over there, right? Is it my zeta? No, no, it's zeta 1, right? Sorry, my mistake. I did it wrong. It's actually plus or minus j omega n, right? So you see, when in differential equations, that chapter maybe in mathematics, we have come across one point where you have a differential equation and you solve it, and you see that the roots of the complementary equation which you write to get a complementary solution becomes purely imaginary, right? Have you come across that somewhere in maths? I get, right. So under that case, you have the oscillations coming up with the solution becoming equal to, if you write an equation to solve this and to find the y of t, you see that y of t is simply a sine function or cosine function. There is it's not going to increase, it's not going to decrease, it's not going to change its uh, any other format, right? So normally we write that solution in general. I am writing in this case. So general format of c of t looks like this. Anyway, we can solve it, but it looks like this. This is 1 minus cos of omega n into t. Okay, so when this happens, right, it's simply 1 minus cos function, right? So I know that cos can have highest value as 1, correct? And right, it can have a least value as minus 1. So when cos is equal to 1, c of t becomes equal to 0. When cos becomes minus 1, this is 1 minus minus 1, so you have 2, correct? Amplitude becoming equal to 2. So the response can be plotted like this. This is the time versus this is c of t for undamped, no damping. Actually, we specifically did not write the plot for this graph. Okay, so the c of t is not written. We'll come back to that. All right. So if this is 2 and if say this is 0, right, we are going to get the oscillations in the following format, because when t is 0, this is cos 0, so 1. So 1 minus 1, it is 0. It starts from 0 and it's a sine wave like this. Okay, so you have some period between this t, right? Omega n is nothing but this 1 by t, natural frequency, which is undamped case, right? So that's why the name suggests omega n is undamped natural frequency. So when there is no damping, whatever is the frequency with which you get oscillations at the output, that is called as undamped natural frequency. Okay, this is the first case. All right, so this actually is the first case, but anyway, for us it is the second case. So then we go for the critically damped case. This is the next case, that is when zeta equal to 1. This is said to be critically damped. So this case is said to be critical damped. Now again, we can actually substitute the zeta equal to 1 and we can try to solve it. So we know that the zeta is 1. So what happens to the transfer function? T of s is equal to omega n square divided by, so this is s square plus 2 zeta omega n. So 2 into zeta is 1. 2 zeta omega n into s plus omega n square. So this becomes equal to simply omega n square divided by, you see denominator is a perfect square. So this is s plus omega n the whole square. Okay. So if the input is equal to, what I can say if it is unit step, right? If r of s is equal to 1 by s, then the c of s will be equal to the same term, omega n square s plus omega n whole square. This is into, yeah, so I have to multiply this well, 1 by s. Anyway, so it's a standard procedure of partial fractions, and then you come back. Okay, so I directly write the answer. So c of t comes to be equal to 1 minus e to the power minus, sorry, there is no zeta. So this is simply omega n t into, this is 1 plus omega n into t. Okay, so we can apply the standard Laplace inverse to come back to this. Okay, now if you look at the plot, what is important is the plot. So the plot here is like this. T versus C of t. So my input is u of t, so it's like, say, this is 1. Okay, so I can see that there is an exponential term, right? E to the power minus omega n into t, right? That is actually getting subtracted from 1. Okay, when this, you tell me what happens to when t goes to infinity? When t is, it becomes 0. In the sense, my output becomes equal to 1 only at t equal to infinity, correct? So this is going to be of the following shape. All right. This is 1. So output reaches 1 at infinity. Right? This is the response of the system. Okay. And we go for the fourth case now. So the fourth case is called as overdamped. Overdamped case where the zeta value is much greater than 1. Right. Now, so we will be having the C of t like this. Okay, so okay, I'll directly write the C of t. Again, we can substitute and we can calculate that part, but for the time being, let's write it in this way. So C of t is given by 1 plus omega n divided by 2 times root of, this is zeta square minus 1 because zeta is bigger, e to the power, we have two terms coming up. First root s1 times t divided by s1. I'll tell you what is s1 and s2. So minus e to the power, this is minus s1 and minus s2t divided by, this is s2. So here the s1 is one of the root. So if you remember, we already have written a root. This is minus zeta omega n minus omega n into root of, this is zeta square minus 1. You see that now the zeta is bigger, so you don't get a j over there. Okay, are you okay? So this is the term. So this is minus zeta omega n plus omega n into root of zeta square minus 1. So we have to substitute this over there to get the final output. Anyway, that's fine. So overdamped and critically damped or underdamped are not given much importance, right? I'll tell you the answer why in the next minute itself. Okay, so let's draw this graph just to see what happens. So this is the t versus c of t, right? So I can see that there are two exponentials controlling this output, correct? So one is e to the minus s1t, e to the minus s2t, right? So I just to make things very clear or easy, what I can do here is that I can compare this output with the previous output. So previous output had how many exponential terms? Only one exponential. So this was providing a delay like this. So my input is something like this, my output comes like this. Okay, so actually this is it, there is a delay between the input and the output, correct? So this happened just because there was one exponential function. But now you see I have two exponential functions, right? So the, if at all my underdamped or critically damped function was looking something like this, right? So let me assume that this is how it was. It was giving an output like this. Now there are two exponentials, so because of which my output is further delayed. Okay, so because you have two different exponential functions, even if you generate such functions and you keep substituting those values, right? right? Maybe for a program or something, right? We can compare it by using the similar techniques. We'll see the same outputs, right? The first function is having some delay. That itself is not acceptable because your function attains the expected output value only at t equal to infinity, right? Okay, now let's come to the important part, that is, okay, what are the problems? Let's see now. Okay, what are the problems with the other three functions? So, what is the input here? Let's go for the first case, that is the undamped condition. So the undamped condition, it says that you are going to get a signal like what is plotted whenever you provide the input like this one. So what is the input? Input is 1. And when the input is 1, we are looking at an answer, the output, which is also equal to 1. Okay. But you see, do you get a fixed value equal to 1 at any point of time on this graph, right? It's never. Even if you wait for infinitely long uh, duration, right, your output will never reach that. Okay, so that's why the answer is no for this. We are not going to prefer this particular condition whenever we design a second order system. So undamped condition is avoided. Okay, then let's go to the next case, right? So this is the one which is zeta is equal to 1, critically damped condition, right? Now anyway, I can see that this is going to reach 1 at some point, right? But what is that point? That point is only when t is equal to infinity. So it's something like you are designing a system. You give the input now, but to get a proper output, you have to wait till infinitely long duration. Again, is it acceptable? No. So you cannot use this. So that's why even the what you call critically damped condition is not acceptable whenever we design a system which is a second order system. Okay, when that itself is not acceptable, there is no question in accepting this, right? So the over damped condition is also ruled out. Okay, now, so what is the solution, right? So we may think that, okay, this the one which we left out, right? So that is the under damped condition may be a solution, right? Okay, but let's look at that now. So again, this answer, the under damped condition, is also not an answer. All right, because what we draw now, you will understand from there. But there is a hope saying that, okay, under some condition, if I accept something, maybe it is close enough. Okay, it's not a perfect answer. Maybe it generates a close enough answer for us. Okay, now, so let's look at the various, okay, let's look at the graph first. All right, so before drawing the graph, let's go back to the equation. So, okay, if this is the C of t which I want to plot, clearly there are two different functions. One is e to the power this term. What is this? This is a, we call that, this part is called as a decaying exponential, correct? Because we know that zeta is always positive, between 0 and 1, and omega n is a positive quantity, right? So we already know that we cannot consider the negative frequencies because of the obvious reasons, and time is definitely positive quantity. So because of that, the minus zeta omega n t is always going to be a e to the power, that term is a decaying exponential. So plus I have to draw one more function, that is a sinusoid. So two functions I need to plot. Okay, and whatever I plot is actually 1 minus that. Whatever is my value, I have to subtract it from 1 and I have, okay, all right. So there is a sine wave coming up and there is a exponential term also coming. Okay, so let's look at that now. So let me assume that, okay, I'll draw another curve maybe at the center. This is what is my input. Okay, so let me consider this as my input, right? We consider that this is unit step, so this has to be 1. So this is 1. input. So this is the output. So I'm trying to plot the C of t. Right. Now there are multiple aspects which I need to consider before I draw this. So there is a sine wave getting multiplied by e to the power. Correct. So the e to the power is a decaying function. So that e to the power function acts like your envelope. Okay, it's an decaying function, but since it is a sine wave, sine function will get enveloped on both the sides, because sine becomes positive, sine becomes negative, plus one, minus one, plus one, minus continually. It actually oscillates between the two values. Correct. So because of that reason, I have to write another envelope on this side. Okay, only since it is a sine wave, I have to do this, otherwise only one side is enough. Okay, right. Now, so put t is equal to 0, right? Whenever I write t is equal to 0 in this equation, because time is 0, right? So this whole term becomes, this is uh, omega nt into t is 0, correct? So the time becomes 0, e to the power 0, that is also 1, correct? So I get a value which is, right, whenever I try to write that value, it is coming closer to 0 ultimately, though there is a small value of zeta, right? So that zeta value comes, right, gives you an answer which is closer to 1. So 1 minus 1, the whole term, this becomes close to 1. So 1 minus 1 is equal to 0. We can even try that for a smaller value of zeta. Okay. Okay. So because of that, my answer actually starts from 0 and it goes in the following fashion. Okay. So the one which I'm plotting now is it actually goes like this, comes down, goes up, and like this. All right. So this is what is the case. So I have one more question now. So is it acceptable, right? Because previously we had we had three different cases where we directly rejected the answer, saying that either it is never going to reach the desired output, or it's going to take a very long time to reach that, right? We told something like that, correct? Because of those reasons, we told that, okay, though they are not acceptable. So my next question now is, right, is this acceptable? That for that, once again, I need to check the equation, right? Only when you check the equation, you can say. Now, when the second term becomes 0 is my question, right? Only when this second half, this half becomes equal to, right, whenever that part does not exist, in the sense whenever that is 0, I can say that yes, answer is only the first term which is equal to 1. So when this is going to happen, no, zeta is fixed, because if you make zeta is 1, it's a completely different case, correct? It's not this case, right? So only control you have is over t. Omega n is fixed, zeta is fixed. Maybe how much longer you need to wait is my question. And is it acceptable will be the second question, right? If I say, maybe the obvious answer which I can see is that e to the power minus zeta omega n into t. So make t is infinity. Yes, definitely. So when t is infinity, e to the power minus infinity, which is 0. So the whole term becomes equal to 0. So, right, again, as I told you, this is also not an acceptable answer, right? But we can make some modifications and we can say that result becomes acceptable under some things. Okay, so I'll tell you now, now that part. Okay, so now you see that this actually has some oscillation till infinity. So again here, in order to get the exact value as 1, right, you have to wait till infinity. Until there, you have an oscillation. Obvious. Okay. right? But what we do now, we introduce the concept of tolerance, right? So compared to the previous cases, like the first case, there was continuous oscillation, it will never come to the desired value. So anyway, that is completely ruled out. Then we wrote the the critically and over damped, which will take really infinite time to just to touch your one. It will never come to one at all in that case, correct? So that's why we ruled out those two completely. But here you see that it is actually it's going to reach one several times, correct? It will reach the desired value, isn't it? It will reach the desired value. So what we do, we define a specific term called as a tolerance, right? Tolerance is something like, okay, I'll change the color to draw the tolerance. It's actually, you say that you define a band, right, around your desired value, something like this, maybe, right? Something like this, and same thing goes on the other side. Let's define this, let's call this as a tolerance band, right? In the sense, the tolerance is something like, if your if your output comes within this band and stays inside this band forever, it will, right? If it will never cross that once again, like not like this. You see, it enters here, but it goes out. It enters, but it goes out. So not these cases, right? So maybe the next cycle you compare, maybe after this. So it actually at this point you see it enters, but it stays within this, right? So you see that it is inside this, right? If this happens, the actual design engineers will consider uh, such a point on time axis as, okay, the system reached, right? System has entered, or system is giving you the approximate desired output. So you can say that output becomes equal to 1 at this point. But because after this it is definitely this is oscillatory, but you can see that it's within the tolerance band. Okay, so the tolerance could be something like 2%, 5%, etc. If for example, if it is say 5% tolerance, maybe this becomes 1.05 and the lower one becomes 0.95. So 5% tolerance is what we call this, right? So there is a tolerance of 5% in the, so this tolerance also becomes one very important aspect of design of the system. Okay, tolerance. Okay, so coming to the next aspects. So let us see. Uh, okay, so it starts from 0 and it reaches the desired output for the first time, right? So where that is happening, that is happening over here, correct? It's reaching that value for the first time. So that time taken to do that, so this is the time axis, is called as a raise time, TR. Time taken by the output to reach the desired value for the first time is the raise time of the system. Again, this is the specific feature of a second order system. All right, what is the raise time is very important, because if you design a system which actually has the raise time like this, you see that this is there is a lot of delay, right? Raise time is bigger, correct? That should not be the case. Raise time should be kept as smaller as possible whenever we design. That's why raise time is one important aspect. The next aspect is the time taken to reach the maximum possible value, which is the first maximum. Okay, so this time, so first time is TR, second one is TP, it is a peak time. Okay, then we have, yeah, for the first one, right? First one itself is a maximum. After that, you never get that kind of high after this. Okay, then we have another parameter, that is the measurement of this point, how much you overshoot. So actually my desired value is 1, right? So from that 1, how much will my output actually overshooted? This shoots something more than that, right? So that is called as maximum M, peak for P, overshoot, MP. Above 1, how much you overshoot. Okay, that is MP. Then we already have defined the parameter called the tolerance, right? So when your actual output enters inside the tolerance band for the first time, right? Enters inside and stays inside. That is called as a settling time TS. So in order to design a second order system, the parameters which we have to use are these four. So for a given system, we need to use these four parameters. So, right, so TS is called as what? That is the settling time. So what is TP? This is peak time. TR is the rise time. And what is this MP? MP is maximum peak overshoot.